I truly hope you've enjoyed today's sessions and tracks. To close out day one, I'd like to introduce Danah Boyd, founder of Data and Society and partner researcher here at Microsoft. Danah's work is focused on addressing social and cultural inequities by understanding the relationships between technology and society. This is such an important area of research. We have the opportunity to better leverage data to achieve beneficial outcomes in society. But, as with any technology, we need to balance opportunities and risks. In this afternoon's plenary session, Danah will discuss the role of data in decision-making, issues of data legitimacy and security, and the role of uncertainty. She'll then close with a conversation with her colleague, John Abowd, about the use of new technologies in the US Census. And now, Danah Boyd.
331,449,281. According to the US Census Bureau, this is the total residential population of the United States as of April 1, 2020. That number is also a form of data theater. Statistics in their original form is the state's science, statistics. The original name, by the way, was political arithmetic. Today, we distinguish state statistics by calling them official, but they are data in the oldest of senses. The Latin root of data comes from a notion of the givens. The state is producing statistics that are then given to the public as data. And those givens are treated as facts. When statistics are understood as facts, the public expects exact knowledge, precision. A census is supposed to be an enumeration of the public, a count of all the people. The Census Bureau produces numbers as facts, knowing full well that such a number is only the best number that they could produce given the procedures that they use. But just because the process worked does not mean that the result is as exact as that number implies. The Census Bureau could tell the public that the total population is, 331 million and a half. The rounding would communicate a certain level of uncertainty. They could also offer up a number with digits after the decimal point, conveying that there are models underlying the data. But they do not. They produce precision because precision signals authority, because precision is a norm and an expectation, because there is pressure to be precise. Now, you might not think that the census is interesting or relevant to what you do, but if you care about data of any form, the census matters. Censuses are the backbone of countless data-making practices. Any data that is nationally representative is pegged to a country's census. If you've ever paid attention to a country's GDP, employment rates, or housing, that country's census data are inevitably inside. If you've tracked COVID rates or vaccine information around the globe, once again, census data is likely at the root of that information. Statistical agencies are charged with producing official statistics for use in public policy decisions and research. In the United States, census data are used to apportion political representatives and distribute funding. In other words, censuses are explicitly and constitutionally democracy's data infrastructure. But even when political representation is not directly tethered to census data, such data are highly political and deeply contested around the world. This is true in many countries where knowing information about the population is as much about politics as it is about accounting. And it's precisely what drove the United Nations to create a statistical commission in 1947 to formalize international standards in official statistics, to help promote professionalization of national statistics in order to help statistical agencies resist political interference. But the professionalization of national statistics also created an important question. What are statistics when they can no longer be political arithmetic? And what do all who are invested in data imagine statistics to be? Now, in most technical communities, it's easy to think of statistics as objective, scientific, mathematical work. The ideal of objective information exists because decision makers find comfort shifting responsibility onto data. This allows people to sort of avoid the politics of data and the politics of decision-making simultaneously, to pretend as if the involvement of data will make things neutral. But this is dangerous thinking, and this is how data become weaponized. But objective framings also obscure the deeply political origins of many techniques we now take for granted. By the way, data scientists, next time you do a regression, remember that that technique was developed by the same man who invented eugenics. His interest in this technique and the naming of this term was not benign. For all of those dubious roots of many methods and practices in statistics, the development of mathematical statistics also opened up a deeper appreciation for how we can understand the limits and biases of any analysis. For example, in the 1910s, a group of Black clerks at the US Census Bureau began calculating the undercount of Black people in earlier censuses. This opened up new possibilities for remedying operational procedures that produced the differential undercounts that were calculated. As statistical techniques became more advanced, scientists also began imagining how mathematical interventions could repair weaknesses in data. Throughout the 20th century, as the field of statistics became professionalized, more and more government agencies began imagining how scientific advances could benefit their mission. Recognizing the possibility of producing higher quality statistics, government agencies began deploying scientific advances to improve the quality of the data. But, in the US at least, this work was often met with significant political resistance. For example, the Census Bureau introduced sampling to reduce the burden on respondents asked to answer numerous detailed questions. But by 1957, Congress barred the Census Bureau from using sampling in key data products. Recognizing the significance of missing people in the count, the census began leveraging data from other sources and building models to fill in gaps in data using a technique known as imputation. This too was challenged in court when the state of Utah argued that the census had no right to impute data, both because sampling was statutorily forbidden and because imputation would violate constitutional requirements of actual enumeration. Now, this was politically framed as fake data or junk science. The Supreme Court rejected these claims, arguing that imputation was not a statistical method, but a technique that improved the count. Yet, in making this claim, the High Court also became an arbiter of statistical methods. Statistical agencies are required to produce high-quality statistical knowledge. But who decides what constitutes statistical knowledge? Those who are invested in modern statistics and advancing science presume that the goal of a statistical agency is to create mathematically valid statistical knowledge, that the output of a census should be the best proximate quantitative depiction of the country as possible. But not everyone sees the concept of statistics in this light. For those who envision a census as a count of all the people, data in a census that does not directly reflect a person is considered suspect. From that vantage point, the work of a Census Bureau is to focus on the act of counting and then reporting what is counted. The goal is the best count, not ideal data. This distinction, as we will see, can quickly become extraordinarily messy. The moment that data matter, those data can never be neutral. The greater the stakes, the less objective those data can be. The very choices of what data to collect, how to categorize data, and how to present data reveal ideological, social, and political commitments. The United States started collecting data about race in 1790 in order to enact white supremacy. But the US still collects data about race because of laws passed during the 1960s civil rights era in an attempt to reclaim census data and use that data as the cornerstone to anti-discrimination and voting rights laws. When institutions collect data, there are politics to what data are collected, and there are also politics to what data are not collected. France, for example, outlawed its census from collecting data about race and ethnic origin in 1978. They outlawed the collection of data about religion back in 1872. This is viewed by proponents as crucial to enacting a race-blind secular society. But critics argue that their failure to collect this data means that France is ill-equipped to grapple with its own inequities and racism. Of course, at least France still does a census, even if it tries not to see certain things. Lebanon, comparatively, last did its census in 1932. Back then, they found that roughly half the population was Christian and half Muslim, split evenly among Sunni and Shia. Lebanese politicians have repeatedly rejected proposals to conduct another census, frankly, because knowing how the population has changed presents significant political risks. Many countries have laws that depend on the existence of data, but that doesn't guarantee that the data will exist. In the US, there's a lot of verboten data, but one might think that if the Constitution requires data, that the US would collect that data. This is not true. After the Civil War, the US passed a constitutional amendment abolishing slavery. 3 years later, the US amended the Constitution again to ensure that people who are born in the United States are citizens and to eradicate the most egregiously racist clause in the US Constitution by ending the practice of treating enslaved peoples as 3/5 of a person. But there's a third data-centric clause to that 14th Amendment that no one ever remembers. It says that should any state prevent a male over the age of 21 from voting, unless convicted of a crime, the federal government is supposed to subtract the equivalent number from the total population of that state, thus weakening their political apportionment. This constitutional amendment presumed that the government could and would collect the necessary data. But in response, Congress has not permitted the census to ask who has been denied the right to vote since 1870. This is an act of purposeful ignorance. Statistics help us know different aspects of our nation, but what we are able to ask about depends on a range of political, ideological, and economic commitments. We have seen this issue on full display recently as countries struggle to collect and produce data about the COVID-19 pandemic. But the politics surrounding data aren't just about what data are or are not collected. Political forces also shape our ability to talk responsibly about the limits of the data. Now, censuses are never perfect. Censuses miss people. They miss people because those people are elsewhere. They miss people because people do not want to be counted. And they miss people because not all people are deemed legitimate enough by the state to be counted in the first place. In other words, censuses miss people for operational reasons, for social reasons, and for political reasons. When official statistics are understood as objective gifts of data given by the state, they are presumed to speak for themselves, to tell their own story. But data don't speak for themselves. They can't. They speak on behalf of others, and what they say depends on the goals and interests of those trying to coax them into speaking. Many powerful people use data to justify their decisions. The objective glean of data gives decision makers cover. Yet when policymakers or executives leverage data to justify their actions, they want data to stay on message. And for data to stay on message, data must communicate precisely and with confidence. Such data cannot reveal their own warts or limitations, raise questions, or offer alternative interpretations. Data must not be seen as weak, for data that are viewed as weak threaten the legitimacy of statistical work. Just as data must stay in line, so must data users. Researchers dissect and analyze undercounts after every census. But when the data are produced, those who want to build policies on them want those facts unsullied by uncertainty. I had a conversation with an applied demographer about how she presented data to policymakers. She recalled a story of her early days working for a municipality where she attempted to communicate confidence intervals alongside her data, only to be rebuffed. Her government client did not want to hear that there could be error in the data, because if there were error, the data could not be trusted. So she was told to come back with facts. Versions of the story are repeated over and over again to me by countless data analysts whose job is to coax data in speaking on behalf of decision makers, both in government and in industry. Now, anyone who has worked with data has at one time or another asked data to speak for themselves. Just look at the data is a statement of exasperation that happens in both boardrooms and kitchen tables. But how practitioners try to communicate the limitations of data varies significantly. When required to support decision makers who are innumerate, data users often feel most comfortable ignoring uncertainty and error, knowing that such information will only confuse or anger. Those deep in technical weeds cannot comprehend how anyone can ethically work with data and ignore such signals. Of course, there's also an art to presenting uncertainty, knowing that the person receiving the data might either ignore the uncertainty or spin the uncertainty to undermine the data. Just consider the context of political polling, where pollsters dutifully point out that the outcomes were within the margins of error when their predictions were wrong. even though they know full well that their data was presented to imply a definitive outcome, with the margins of error functioning as a tiny little footnote. Or, on the flip side, think about climate scientists who try to responsibly communicate the uncertainty of complex models, only to have their work systematically undermined as lacking certainty. The Census Bureau is expected to produce facts and perform precision, both to appear authoritative and because any responsible scientific communication involving uncertainty can be politicized. The government scientists know that the data have limits. Much of this information is communicated in scientific meetings and in footnotes and metrics, often buried in esoteric files published alongside the data. Government researchers also provide follow-up analyses after publishing their data. But by and large, those who rely on democracy's data infrastructure tend to ignore signals of uncertainty, error, or noise when using that data. Some ignore it because they don't know how to work with such information. Others ignore it because their clients want to hear facts and precision. Still others see the very discussion of uncertainty as creating the risk that the data will be delegitimized. Yet, in my mind at least, the illusion of a perfect census has become more costly than people realize. Without being able to grapple with the limitations of data, the Census Bureau is unable to get the social and political support to introduce new techniques that can systematically improve federal statistics. This is particularly costly in a social context in which getting people to self-respond and share information with government representatives is getting increasingly challenging. The scientific community has developed a range of techniques to improve data quality in spite of data collection limitations. But embracing these requires that stakeholders understand data's limitations and vulnerabilities. One reason why census data are imperfect is that the public doesn't always trust the government to be a data caretaker. Since 1840 in the US, those conducting the census have known that privacy is key to getting people to participate. For the census, statistical confidentiality is a key requirement for procedural, legal, and moral reasons. The procedural imperative has only grown since 1840, with numerous studies repeatedly showing that people will not respond if data can be identified. For over a century, there have also been legal requirements that prevent census data from being accessed for non-statistical purposes. And more recently, as scholars have uncovered how census data were used in the US and Europe during World War II, there has been an increased commitment within the statistical community towards data privacy more generally. To achieve statistical confidentiality, the Census Bureau has been evolving its disclosure avoidance procedures for years. Initially, the government simply chose not to publish certain statistics, but by the 1980s, the Census Bureau was facing significant pressure to publish more detailed data. So, in 1990, the census began injecting noise into the published data in order to publish small area geographies. The noise that was injected was not systematic, but edits designed to smooth outliers from visibility. This should have made statisticians cringe, but few knew that this process was happening, and to this day, no one outside the Census Bureau knows much about the level of edits that took place. Meanwhile, computer scientists began showing that these kinds of edits provided little protection. These same computer scientists also began developing other techniques to improve this, such as differential privacy. Now, differential privacy is nothing more than a mathematical definition. It is a framework for being able to evaluate how much information about individual records is leaked from statistical data. By introducing statistically unbiased noise into data, a system based on differential privacy can try to maximize statistical confidentiality and high-quality statistical output. The allure of differential privacy to those invested in statistical confidentiality is that such a technique is future-proof. No matter how much new information is introduced, a system that is managed through differential privacy can only leak as much information as it was designed to leak. There are numerous ways to implement differential privacy, but all involve Greek letters serving as variables that govern key aspects of the system. One of these letters, epsilon, represents the privacy loss budget within a differential privacy system. Think of this as a knob. Turn the knob one way and the data are noisier, but have higher privacy protections. Turn it the other way and the noise recedes, but the data become more vulnerable to attacks. Systems that rely on differential privacy are designed to enable decision makers to manage the amount of noise introduced in order to strategically balance the privacy of individual records and the reliability of statistical calculations. But differential privacy takes 4 things for granted. First, it presumes that publishing usable statistics while protecting the confidentiality of underlying data is imperative. Second, it presumes that usable statistics can be understood in mathematical terms. Third, it presumes that data users find value in knowing, understanding, and measuring noise, error, and uncertainty. Fourth, differential privacy presumes that transparency is desirable. The Census Bureau began integrating differential privacy into its scientific products in 2006, making previously inaccessible data available for the first time. The scientific community cheered. But the decennial census is a different product than other data products produced by the census. And so when the Bureau decided to modernize statistical disclosure systems for its canonical product, they failed to appreciate how much backlash they would receive. The Bureau relished the ability to be upfront about its procedures. Scientists imagined that this would allow for better governance of the statistical system, better accounting for uncertainty. They thought users would be pleased. They were wrong. Lawsuits began even before the census data were released. More are expected. Once again, we can expect the Supreme Court to have to grapple with what statistics are. Some opponents to differential privacy have scientific concerns, but many of those who are challenging the Bureau's right to modernize its system do not see census data through the lens of mathematics. They want data to be facts, to speak for itself, and they see differential privacy as an abomination for daring to alter data in the first place. To complicate matters more, there are also people who see political opportunities for fighting the Bureau, regardless of the ramifications to statistical work. Transparency is an ideal that is common in computer science, especially in areas birthed from cryptography, which holds a deep moral commitment to transparency. Likewise, mathematicians and computer scientists see uncertainty not as something to avoid, but as something to actively embrace. Within this way of seeing the world, advances in scientific method to improve data quality and negotiate statistical confidentiality are a statistical boon. But they are also a political nightmare. Epistemology is the study of knowledge, how we know what we know. Science is the pursuit of knowledge through rigorously defined methods and practices. Scientists have historically been convicted of heresy, burned at the stake for their beliefs, but in the 20th century, scientists have achieved significant prominence in many societies. Unfortunately, their rise in stature is not always well received, especially when scientific findings are viewed as economic or ideological threats. In the 1980s and 1990s, scientists weren't physically tortured, but their practices were regularly hijacked, often under the guise of sound science. The most blatant abuse of scientific processes unfolded in the fields of climate science and public health, as the oil industry and tobacco industry worked to seed doubt about scientific consensuses on climate change and cancer. More than anything, these efforts perverted scientific uncertainty to enable analysis paralysis and make action impossible. In the 90s, a group of scholars came together to try to make sense of what was going on. They coined a term, agnotology, to describe the study of ignorance. What they argue is that ignorance is not simply what we don't yet know, as in science. It also refers to knowledge that has been lost, as well as knowledge that has been purposefully polluted. Uncertainty is central to scientific work, but in a public policy context, uncertainty is seen as toxic and dangerous. The politicization of uncertainty to undermine scientific consensus during this period is part of why those seeking to ensure the legitimacy of federal statistics often default to rejecting any information that might undermine confidence in the data. Today, policy-oriented people don't want to talk about uncertainty because for 20 years they watched uncertainty be used to undermine scientific knowledge and evidence-based policymaking. Census data are the product of scientific work. They are also infrastructural in our society, core to countless policies and practices. Lives depend on that data. Economies depend on that data. Public health depends on that data. Those using census data want to know that they can trust the data. that they can rely on that data in their calculations. Scientists who work on those data are obsessed with quality, but they know they've never been able to produce perfect data. Yet the more that data are politicized, the more perfect they are expected to be. And the more perfect they're expected to be, the more those invested in the legitimacy of the data are expected to suppress any discussion of uncertainty, noise, or error. In the process, an illusion has been born. Now, drawing on the work of other scholars, I can't help but think of this illusion as one type of statistical imaginary. In my mind, a statistical imaginary forms when people collectively construct a vision of what data are and what they could be. For example, when the US constitutional conveners imagined conducting a census to anchor a democracy, they were creating a statistical imaginary. Corporations also produce statistical imaginaries. For example, when companies create advertisements talking about all of the benefits of big data and AI, they're producing a vision, a statistical imaginary. Now, statistical imaginaries don't have to be far-fetched fantasies. They don't even have to be illusions. They can be deeply grounded in practice, rooted in pragmatic goals, and realized through technical systems. But they can also become unmoored from practice when the illusion of what statistics should be is more appealing than the reality of what it is. Machine learning, for example, is a powerful tool, but the fantasy that machine learning can solve all of societal problems is completely disconnected from reality. The key to responsible data science is to keep statistical imaginaries in check. Many famous people have spoken about the dangers of lying through statistics, contorting statistics to say ridiculous things. There is also a danger of producing a statistical imaginary that can't be realized. Responsible data science requires us to ground these conversations. Yes, data must be sound, but so too must be the technical, cultural, and political logics that surround the analysis and use of data. All data are made, not found. The notion that data can be the product of an apolitical act of counting, it feels warm and fuzzy, but it is an illusion. And that illusion obfuscates how data categories are politically contested, how choices in collection and processing require human decisions. But the biggest problem with this illusion is that it encourages those involved in data work to ignore the limitations of data in order to appease an ideal of objective facts. Data cannot be treated as givens. Their imperfections and contexts must be lovingly embraced. Engaging with uncertainty is risky business. People are afraid to engage with uncertainty. They don't know how to engage with uncertainty, and they worry about the politicization of engaging with uncertainty. But we're hitting a tipping point. By not engaging with uncertainty, statistical imaginaries are increasingly disconnected from statistical practice, which is increasingly undermining that statistical practice. And that threatens the ability to do statistical work in the first place. If we want data to matter, the scientific community must help push past the politicization of data and uncertainty to create a statistical imaginary that can engage with the limits of data. As technical researchers and scientists from around the world, y'all have a really important role to play. We owe it to our respective communities to ensure a more responsible data future. This means that we must resist fantasies that surround data in our present world and help ground the data work that is emerging. Many of you are already committed to producing metadata about data sets to render visible the features of that data. This should be standard practice. But take it a step further. How are you working to understand how data is being used? And what are you doing to ensure that data is being used responsibly? The politicization of climate data and cancer data 20 years ago should have been a warning. The politicization of data is now all around us. It threatens the legitimacy of democracy's data infrastructure. It threatens the ability to understand public health crises. It threatens the ability for individuals, businesses, and governments to make informed decisions. Many of you here today are tool builders who help people work with data. Rather than presuming that those using your tools are clear-eyed about their data, how can you build features and methods that ensure people know the limits of their data and work with them responsibly? Your tools are not neutral. Neither is the data that your tools help analyze. How can you build tools that invite responsible data use and make visible when data is being manipulated? How can you help build tools for responsible governance? Some of you here today are critical scholars, watching all of this unfold. We have all seen technologies be used to enact abuses and reify structural inequities. But let's also be careful. In some contexts, our critiques are getting twisted around to undermine data infrastructures that uphold democracy and civil rights. Context matters. Yes, we need to critically interrogate how technology upholds systems of power. But we also need to be cognizant of who benefits from seeding doubt and undermining science and statistics. Census data are a canary in a coal mine. The controversies surrounding the 2020 census are not going to go away in short order. The statistical imaginary of a precise, perfect, neutral data set has been completely ruptured. There is no way to put the proverbial genie back in the bottle. And nothing good will come from attempting to find a new way to ignore uncertainty, noise, and error. The answer to responsible data use is not to repair an illusion. It's to constructively envision and project a new statistical imaginary with eyes wide open. And this means that all who care about the future of data need to help ground our statistical imaginary in practice, in tools, and in knowledge. Responsible data science isn't just about what you do. It's about what you ensure all who work with data do. Thank you.
Danah, thanks so much for a fascinating talk. It's so important to understand how our work in technology situates in a broader societal context. Along those lines, you alluded to a unique and important set of research challenges around the role of data and uncertainty in decision-making. What inspired you to get into this work?
Thank you. I started out as a computer scientist, and then I retrained under a group of anthropologists so that I could study social media. Along the way, I ended up tracking how young people were using social media, and it got me really curious about privacy. Many people were making statements about kids, they don't care about privacy. And I was like, actually, all my work says they care deeply about privacy, but that there was a disconnect between how we understood privacy from a technical sense and how it was experienced on the ground. And so that curiosity about privacy led me to many different paths, including trying to understand what was happening with differential privacy.
Yeah, let's pick up on this point about privacy. So you talked a lot about the role of uncertainty, the importance of conveying uncertainty, and maybe even the role of technology in helping to reduce uncertainty in different ways. On the other hand, uncertainty can be useful for privacy in particular. So how should we think about trade-offs in that space?
I'm super excited by all that's possible with statistics as we're seeing it unfold. And uncertainty is one of those areas where harnessing and understanding uncertainty can allow us to have that buffer. And there's tremendous work happening across Microsoft on privacy-preserving machine learning, which is really trying to embrace formal privacy, considerations, and also trying to think about how to empower all sorts of data users to be able to do sound statistical work. There's also some really interesting work happening trying to think about spreadsheets, right? All of our amazing work on Excel, but what can we do now if we can help all of the users better understand the limitations of their data? This gets me really excited to see the possibilities, but a lot of it is about what we know as scientists, as computer scientists, as statisticians. We need to prepare the world of data users, the world of people that we're showing that data has potential, to also grapple with that uncertainty. And we can do that through our tools, but we also have a lot of educational work that needs to happen.
And you've had a unique vantage point, really watching how some of this is playing off with the US Census. Can you share some of the insights gained, some of the conversations you've been having?
No, absolutely. So I've been lucky. So I'm an ethnographer, and that means that my responsibility is to map cultural practices. And I realized that the census, as it was, working towards the 2020 census, was going to be struggling with all sorts of new challenges, in a data-centric world. And so I had the great opportunity to dive in and really observe what the government agency was doing as it tried to make this census work. And this, of course, started before a pandemic, and then trying to make it all happen, through the pandemic. And part of it is I'm super delighted that I spent so much time with John Abowd, who is the chief scientist at the US Census Bureau, as he tried to work with the government agency, empower all sorts of people to really modernize a whole slew of statistical processes. And I'm delighted that we have an opportunity to spend some time with him today.
Absolutely.
Hello and welcome. I'm sitting here today with John Abowd, the Chief Scientist of the US Census Bureau. John is also a Professor Emeritus of Economics, Statistics, and Data Science at Cornell University. But in 2016, John left his cushy academic position to become a civil servant inside the government in order to help strengthen the methodological work of the Census Bureau and lead a range of innovative efforts, including the deployment of differential privacy. I've asked him to join us here today to put his efforts into a broader context. Thank you, John.
Thank you for inviting me.
In my talk at the top of the session, I spoke of what people imagined official statistics to be. I was hoping you might be willing to start by putting official statistics into context. What are they? Why do they matter?
So, Dana, that's an interesting question, and not one actually that I thought about in my academic job as much as I have here. There's a kind of a big three for official statistics. Your population, how many people live here, your national income accounts, how much is produced, and some summary measure of health and general well-being. Those take lots of forms, but they're generally health statistics. So governments all over the world use that kind of data, and official statistics grew up producing that kind of data. So basically that's what they are. They're how many people, how much do they produce, and how healthy are they?
And why do they matter?
There's a lot of different use cases. The most straightforward one for the population is that in many governments, some population measure is used to allocate political power and resources, either explicitly or implicitly. Big cities get more resources than small cities, even if it's managed by something other than a democratic process. Measures of economic well-being, national income accounts, unemployment rates, generally grew up as ways of comparing the relative wealth, or I don't want to call it full well-being because they leave a lot of things out, but as a quantified way of describing how the economy is working and whether it's in good health or not. And then general health statistics are used for many purposes, but often to project how many people are going to be of certain ages at different points in time, and a lot of social welfare systems are based on those kinds of projections.
Well, super fascinating. And one of the things I've noticed, you come into the government to help modernize the aspects of the statistical system. What does it mean to modernize federal statistics?
So this question has a long technical answer that I'm going to partially spare you. But in statistics, as it's understood in official statistics, there's a way of thinking about the problem. And that way of thinking about the problem was designed to make the answer that you get meaningful and trustworthy. And so the way the official statistician thinks about the problem is that there's some thing that you want to measure. And we call it an estimand. And you can think of it as how many people were alive in the United States or China on some given day. And that seems like a perfectly well understood estimand. So we can start there. It defines what you want to count and the universe you want to count it from. That process of the universe you're counting it from is statistical estimation. And so statistical estimation produces an estimate of the target quantity, the estimand. In official statistics, there is a very well understood way of going about this for many of the things we try to measure. That has its origins in the 20th century sampling and the statistics that you talk about in your talk, pointing out correctly that some of the fathers of statistics did not have the best motivation for some of their work, but that work shapes the way statistical agencies think about a problem. But it is monumentally expensive, and it is very difficult to execute to get more granularity. So I don't just want to know how many people live in the United States, I want to know how many people live in every square kilometer of the United States by square kilometer, for example. I don't want to just know how much is produced in manufacturing in the United States. I want to know how much is produced by every detailed manufacturing classification. And I don't just want to know it once a year. I would like to know it every day, okay? So that increased demand for granularity and timeliness is being met. It's being met in the private sector with statistics that are generated from the information age, from the fact that virtually everything that we do or touch has a native digital image. And that native digital image can be used to supply statistics. You need to figure out a way to fuse the trustworthy way of gathering this information and summarizing it with the massive amount of available information so that you can be more granular, be more timely, but still be trusted.
You know, phenomenally challenging. One of the things I've noticed in industry is that, often sloppy data is just par for the course. Most people think, it's good enough. And one of the things I've been struck by inside the census is how critical high quality data is. And as you're talking about the importance of modernization, one of the things that impresses me is just the importance of really focusing on, improving the processes and making certain that quality is at the center. So as the chief scientist, you've gotten to push innovation to be part of this. But what makes that challenging, or where is that different than what people in industry experience?
So I have an example that kind of illustrates the point, and many of our listeners have possibly heard of this. It's called Price Stats. Price Stats is a modern tech information company, but it grew out of a research project at MIT called the Billion Prices Project. And it supplies price indices and purchasing power parity indices. And among its biggest clients are central banks, which basically can't get this kind of information any other way or any practical way, especially not as timely as they can produce it. But it involves processing trillions of transactions in a very obscure, non-transparent way. And stat agencies can aspire to do that. They can aspire to having the infrastructure to do that kind of computation and to understanding what's supposed to be measured. But it takes a while, sometimes a long time, to get the trust and confidence in the underlying number. So we use the Consumer Price Index. Our national pension system is indexed using the Consumer Price Index. And that is a statistic that is produced regularly by the Bureau of Labor Statistics with a very transparent methodology. And there's a lot of field work and other things that go into it, but with a very transparent methodology. And the people who index to it can rely on it, and they can rely on this month's being comparable to last month's or on having multiple years to adjust to a change in the methodology. We have to get from, that's the only way to think about this problem, to we can use some of the high-tech data assets. We can make enough of it transparent and reproducible to inspire confidence, and we can benchmark it to something that gives confidence. The way that people got confidence in price stats is that it benchmarked to the consumer price indices in a number of different countries and showed that that it could track them. It was also using some of the more expensive data about expenditure patterns, which these transaction databases don't have. So you have to estimate that, and that estimation process also has to inspire confidence and be sensitive to changes in the underlying environment.
When we think about, building confidence and think about estimation, there's always some data that's not quite right. Data are imperfect. And one of the things I've been struggling with is that there doesn't seem to be a lot of room for conversations about uncertainty with data. How do we grapple with uncertainty in a more sophisticated and nuanced way in our data-driven world?
That is a challenge. And it's particularly a challenge if the use case for a particular statistic requires more precision than the accuracy of the statistic. And you touch on this in your talk. My favorite example is the population census of the United States, where the use case is to allocate the seats in Congress. And the formula requires that you give it a statistic down to the units column. So that's 9 digits of precision in the population. Well, the instrument, which is the estimator, the process of conducting a census, doesn't yield data that are accurate to 9 digits of precision. So you need to have some kind of a compromise. One compromise would be to do the formula with less precision in 10,000s or in 100,000s and have some way of fixing ties. One way would just be to add a seat if there was a tie, take it back at the next census. And that's entirely up to Congress. The Constitution doesn't say anything about how the statistic, the census of population, is to be used to apportion the House of Representatives. It just says, do it the way Congress tells you to do it. And so that has generated the demand for a statistic that is much more precise than its accuracy warrants.
Well, and precision has been, a challenge in this decade in particular. And let's talk about differential privacy for a moment, right? Part of the beauty of differential privacy is that it makes certain that we can manage statistical confidentiality. But in order to do it, it requires the introduction of noise. What's it been like trying to implement differential privacy this time around?
Well, as you know, this isn't the first time the Census Bureau has implemented differential privacy. But in the other cases, on the map, which was the first project we did it in, and then many of our recent new products, almost all of them, in fact, you were going from, there's nothing going to be published here until we get the confidentiality protection system in a modern form right. So you were giving people new data to work with, being honest about its margins of uncertainty, but new data. In the case of the census, we have routinely published hundreds of billions of statistics from that population and a few measurements on that population from about 1.5 gigabytes of data. It was going to have to be combined with some amount of there won't be as much information, okay? And the tool gives you the ability to control your privacy loss, to quantify the confidentiality protection. That's its advantage. But it makes very explicit that, well, it can't be perfect, right? There is some disclosure risk and it's being managed. So the Census Bureau has completely owned managing the confidentiality protection, the disclosure risk for the 2020 census in a global sense, not one statistic at a time, but all the statistics considered as a whole. And that was a very new mentality, and it required that senior executives learn to think about it as a risk management problem and learn to internalize some of the allocation methods that we had to use.
I still think it's pretty phenomenal that the Census Bureau in the United States has taken this really innovative step. And I know many of the people who are with us today are from around the world. We have scientists from different countries, but also people who are trying to think about what it will mean for them to modernize their, statistical system. Based on what you've learned in this process, what would you advise, people from other countries about how to engage or how to think about disclosure avoidance? What would you encourage them to do based on what you've learned?
Well, I think that the lesson I've told people when they've asked that precise question is it's much easier to go from 0 to differential privacy than from I published everything to I quantified how much I was going to allow you to learn. So if you can avoid the second situation, you should avoid it. And I do have some suggestions about how you might avoid it. The first thing is you have to understand how the data are going to be used. And there have to be leading use cases. It's convenient, but fundamentally misleading to say, well, we don't really know all the use cases, so we're going to try to make this work for everybody. That's a mathematical impossibility, and I would encourage the computer scientists and statisticians with us today to not encourage that way of thinking. I would say, we're going to design this information product to meet a certain basic need. There may be other things that people want to do with the same data, and we will reserve some ability to do that, but design the big ones to meet the important use cases. For economic statistics, it's changes in meaningful indicators. For population statistics, it's changes in the description of the population for some level of geographic refinement. Those use cases can drive a lot of statistics. They won't always work for anything you could think of to do with similar data.
Your team built much of this from scratch. And I have to say, I've been totally inspired by all of the amazing hard work all of you have done that's often under-recognized and invisible. I'm curious, as you know, there are tool builders here, there are researchers here. What are the things that you now wish you had? What are the things that need to be built over the next decade?
Wow, that's a really good question. That might be the $64,000 question, to use a really old currency. So the thing that I wish we had had was a more complete description of how the differential privacy framework really constitutes a privacy loss accounting framework, and you should do your risk management within that privacy loss accounting framework. I understood it. The other computer scientists and statisticians who worked with the Census Bureau understood it, but those tools are only just now coming into existence. Those tools can be used to teach subject matter experts exactly what the problematic things that you want to do are. And an excellent example is, I can tell you how many people live here. I can tell you how many households there are here. If you ask me how many people are in the average household, that question is enormously more disclosive, unless I'm willing a priori to limit, well, no household can have more than 3 people. That doesn't seem like a realistic limitation. Okay, well, no household can have more than 100 people. Now, all of a sudden, you've made that query 100 times more difficult to protect. And once the subject matter experts understand why the combining of the two different ways of counting populations creates a special problem, they can think about, well, what are the important numbers to get out of that? In the economic area, the tool you need is, I want to know how many businesses there are so that I can get some idea of where the activity is. But I also want to know how much activity each business releases, either measured as payroll or measured as gross sales. That's a very hard problem, because that statistic you're interested in, it's skewed. And so it is usually the case in economic data that a few of your businesses are generating the bulk of your economic content. A much harder confidentiality protection problem than more balanced situations.
What advice would you give to researchers out there who are listening in? You know, what kinds of things that they should be working on, and what projects would you wish them to engage in? How can they help government scientists in this whole process?
So the first thing I'd say is, come and work for us for a couple of years. You don't have to spend your whole career in a statistical agency, but the best way to learn about what one does is to watch it from the inside, and the best way to contribute is to work with a team. We do almost everything in modern teams the way tech companies do, but we need more people with the toolkit that modern computer scientists, data scientists, confidentiality specialists who are brought up in the differential privacy tradition, the tools that they can bring, we could really use.
Thank you, John. Thank you for being with us today. Thank you for all of the work that you're doing. Thank you for all the amazing work that your team has done. Thank you.
Well, thank you for the invitation. And I want to thank my amazing team too. It took a very large team with a very diverse set of talents to get done what we've gotten done so far. And they're hanging in there, continuing to do the good work. So thank you.